In the previous video, I compared the direct CO2 emissions of combustion engine cars with emissions of electricity generation needed for EVs. Today, I will look at the emissions created during manufacturing of both types of these vehicles. The series will then continue with indirect emissions, such as those from drilling and refinement of oil or building and supplying power plants. I will first compare combustion engine car versus electric vehicle excluding the battery. Then, I will take a look at the batteries separately, as they are the dominant component from the standpoint of emissions. In both cases, I will start with my own calculations, then I will compare my estimates with official studies. Lastly, I will provide some calculation comparing CO2 emissions from manufacturing versus driving. Let's dive into it. Disclaimer: it is impossible to arrive at one precise number. The CO2 intensity depends on the following factors. How big is the car? How efficient is the manufacturing process? How clean is the source of electricity used during the manufacturing? And how clean and efficient is the sourcing and processing of the materials used? With this in mind, I will try to provide at least rough averages. The dominant component in a car is steel. The chassis, much of the car's body, and parts of the engine are made out of it. Steel represents around 60% of the car's total weight. According to World Steel Association, an average car contains 900 kilograms of steel. Production of 1 ton of steel may produce more than 1.5 tons of CO2. However, it depends on the type of production. Primary steel, created from iron ore in blast furnaces and basic oxygen furnaces, produces on average 2 tons of CO2 and as much as 3 tons in China. On the other hand, steel recycled from scrap in electric arc furnaces leaves behind only around half a ton of CO2 per ton of steel. Additionally, when talking about primary steel, you have to add the emissions from mining the iron ore and processing it. The mining by itself is not as CO2 intensive as the subsequent processing and agglomeration of the iron ore, which may together add some additional 300 kilograms of CO2 per ton of steel. You also need some half a ton of coke, so you have to add the emissions from mining and processing the requisite coal, and then transforming the coal into coke through a CO2 intensive process of coking, which may add some additional quarter of a ton of CO2. Not to forget, for both primary and recycled steel, you need to add at least 2 transportations, one of iron ore and scrap to the steel production facilities, and then transportation of finished steel to the car manufacturers. Bulk carriers are the most efficient mode of transportation, emitting less than 10 grams of CO2 per ton per kilometer. Estimates of freight train emissions converge at 20 to 30 grams per ton per kilometer, and trucks emit on the order of 50 to 150 grams per ton kilometer. The total transportation emissions, of course, depend strongly on the distance and combination of transportation modes, but they may range from a few dozen to several hundred kilograms of CO2 per ton of steel. BMW stated in its report that the share of recycled steel in its cars is around 25%. Other car makers pledge to increase the share to some 40% by 2030, which suggests that currently they use similar share as BMW. Taken together, the 900 kilograms of steel needed for an average car might leave behind over 2 tons of CO2 before it enters the car factory. In certain parts of the car, notably the doors, hood or trunk lid, steel is being replaced by aluminium, which has much lower density and can reduce the total car weight. This is desirable because reducing the weight can improve the fuel economy of the cars. However, the production of primary aluminium is much more CO2 intensive than of steel. According to International Aluminium Institute, 1 ton of primary aluminium produces on average some 15 tons of CO2. The lion's share of this are emissions from electricity, so there is a lot of room for improvement, and again, a large variation among countries. But almost 60% of primary aluminium is made in China. Second largest producer is India. Both have very polluting electricity, which is why the global average is so high. Interestingly, recycling 1 ton of aluminium produces only around half a ton of CO2, similar to recycled steel. Currently, around a third of global consumption comes from recycled aluminium, even though from what I've been able to find, the share in the automotive industry is closer to 50%. The emissions from bauxite mining and transportation of aluminium is of the similar order as the iron ore and steel. The average amount of aluminium in cars is constantly growing. The recent estimates seem to converge around 200 kilograms per car. The carbon footprint it leaves behind is on a super wide range, from less than 200 kilograms of CO2 if it came from recycling in a country with clean electricity, to more than 4 tons of CO2 if it was primary aluminium made in China. Taking a very rough average, we arrive again at some 2 tons of CO2 for those 200 kilograms of aluminium. The last material found in large amounts in a car are the various types of plastics. The most common type is polypropylene, especially used for the interior. Another one is polyamide, desirable for its durability and heat resistance. Production of 1 ton of polypropylene resin generates some 1.5 tons of CO2, whereas the polyamide closer to 6 tons. A bit of energy is needed to transform the resin into plastic granulate. The specific plastic components are then created from the plastic granulate in a process called injection molding. This process also produces greenhouse gas emissions, mainly through electricity consumption, on the order of 2 to 4 tons of CO2 per ton of final product. According to American Chemistry Council, an average car contains some 200 kilograms of plastics. So again, depending on large amount of factors, the final score for plastics in an average car may lie somewhere between half a ton and 1.5 tons of CO2 equivalent. Putting steel, aluminium and plastics together, we have already more than 5 tons of CO2. These three make up the bulk of the weight as well as the majority of greenhouse gas emissions. The remainder of the car contains materials like glass for windows, copper wiring for electronics, leather and textiles for the interior, or rubber, not least for the tires. I will now make a jump to the final assembly in the car factory, before returning to the production of the individual car parts themselves. When it comes to the emissions of OEMs, that is the car manufacturers, ACEA, the Association of European Manufacturers, claims that emissions per car produced were some 800 kilograms of CO2. Most of this is once again attributable to electricity. ACEA also mentions that the electricity consumption is close to 3 megawatt-hours per car. Multiplying by the emission intensity of the typical European electricity mix, the estimate of 800 kilograms of CO2 per car seems consistent. Given that other major car-producing countries typically have more CO2-intensive electricity than European carmakers, the global average would probably be over a ton. So what is actually done in the car factory? Much of the car's body is created directly in the car factory from steel and aluminum coils. The body is also painted in the paint shop. And obviously, all the other car parts are then assembled. But the manufacturing of the individual car parts is typically done in other factories, either owned by the manufacturer or by their suppliers. I haven't been able to find decent estimates of emissions of this part of the production chain, except for the approximation of injection molding, but given the enormous complexity and the sheer amount of car parts that must be produced, I think it's fair to estimate that it generates at least as much emissions as the final assembly. This puts my estimate of the average total to some 8 tons of CO2 for a medium-sized combustion engine vehicle with wide range surrounding it. Study by McKinsey & Company came to similar conclusion, saying that the manufacturing emissions range between 5 to 10 tons, and their division of the sources of the emissions is also almost identical. Now, what is the difference between an ICE vehicle and EV, excluding the battery, in terms of emissions? The combustion engine is heavier and much more complex than the electric motor. However, the majority of electric motors still contain rare metals, whose extraction is very CO2 intensive. For example, according to International Energy Agency, mining and processing 1 ton of neodymium produces almost 80 tons of CO2 equivalent, 40 times as much as steel. So even a few kilograms of such metal can offset the difference. So the final CO2 manufacturing emissions of EVs without battery are estimated to be very similar or just marginally smaller than of the ICE cars. The McKinsey study mentioned earlier says it's similar. This graph shows the ICCT white paper estimates for vehicles in the lower medium-size category. So how many CO2 emissions are created during the manufacturing of an EV battery? I will talk about lithium-ion batteries because they are still the standard. New technologies, such as solid-state batteries, are still in more or less experimental phase and are unlikely to become the standard before the end of the decade. The emission intensity obviously depends on how large the battery is, so I will refer to it in terms of kilograms of CO2 per 1 kilowatt-hour of battery capacity. The still most common type of lithium-ion battery is the NMC, nickel-manganese-cobalt battery. An average EV contains some 9 kilograms of lithium, 40 kilos of nickel, 25 kilos of manganese, and over 13 kilograms of cobalt. Mining of these metals is quite CO2 intensive and is connected with environmental and even human rights issues. Still, the material extraction is only one of many processes in the battery manufacturing. Reviews of older studies suggested that the average CO2 intensity of the batteries is around 150 kilograms of CO2 equivalent per kilowatt-hour of capacity. More recent estimates tend to be lower due to both more efficient process and revised methodology. The same McKinsey study mentioned earlier estimates that battery manufacturing produces around 100 kilograms of CO2 per 1 kilowatt-hour of battery capacity. This includes the mining and transportation of the required materials. According to European Federation for Transport and Environment, manufacturing of a battery in China involves some 120 kilograms of CO2 per kilowatt-hour of capacity, whereas in Europe it's barely 80 kilograms. Okay, if we accept that battery manufacturing produces in total some 80 to 100 kilograms of CO2 per kilowatt-hour of capacity, then the production of a 75 kilowatt-hour battery, typical for long-range Tesla, produces around 7 tons of CO2, while the smallest 25 kilowatt-hour batteries might leave behind only 2 tons. And the over 100 kilowatt-hour batteries of large electric SUVs get easily 10 tons. Now let's compare the battery manufacturing emissions with tailpipe emissions. If we assumed tailpipe CO2 emissions of 115 grams per kilometer, equivalent to around 5 liters of gasoline per 100 kilometers, achieved by the most efficient cars in Europe, you can see the kilometrage equivalent to the battery manufacturing CO2 emissions based on the battery capacity. In the other columns, you can see the equivalents for different fuel efficiency assumptions. If you wanted to include the emissions from drilling, transporting and refining the oil necessary for the gasoline, you can cut these numbers by about 25%. That would give you the distance after which the EVs would repay their CO2 debt, so to speak, if the source of charging electricity was 100% CO2 free, which it usually isn't. The higher the emissions of electricity generation, the longer the payback. For example, if the EV emissions were 50% of those of the compared ICE vehicle, the kilometrage required for the EV lifetime emissions to be equivalent would be double. You can calculate yourself using whatever efficiency and electricity emissions you please. You can simply divide the battery manufacturing emissions by the difference between the combustion engine car and the electric car emissions. So for example, if the battery manufacturing produces 7 tons of CO2, which is 7 million grams, and the difference of driving the cars is 100 grams per kilometer, it would take 70,000 kilometers before the cars would break even. Note that all these calculations assume that the battery survives for the entire lifespan of the EV, which is not always the case. I hope you found this video helpful, and I will see you in the next one.